Yeah, yes, Nitin. Now I can see. Yeah, so good. Yeah, perfect. So, in fact, we had very large number of participation. We had around 960 participants. And since our current instance has a maximum capacity of roughly 1,000, so I had to stop somewhere. Otherwise, it was continuously increasing. However, what I am observing is that since these are engineering college students and most of the classes are going on, so sometimes they are not able to turn up. But still, there are roughly 200 faculty members from various engineering colleges from all across the country. So they are there. There are many, at least to my understanding, somewhere around 200 or 230 research scholars might also be there. So at different times, these scholars and people will be joining. So whatever goes on, we will carry on with our talks. The thing is, we are also broadcasting the same communication through YouTube also. So these the talks will be recorded and kept in the repository, so that those students, by chance, if they missed to attend the live sessions, they can, of course, go back. Hi, Raghu. Thank you very much for joining, finding the time for the sessions. Right, so we are really overwhelmed and very happy to have you on. So, let me quickly introduce both of you to the participants. Dear participants, welcome you all. Today's this session, this will be for about 3 hours session, where Raghu and Nitin from Cisco would be talking about cryptography for networked communication. As such, both of them have great experience. In fact, they are living a career which you people have in your dreams. So, congratulations to Nitin and Raghu for being a star performer, so that the students are keen to listen. So Nitin is an entrepreneur with about 11 years of experience in network security, and he is the technical leader in Cisco customer experience team. And he is passionate about learning, creating new things, of course, as an engineer does. And he designs customized customer solutions, drives automation, innovation, and does a lot in the area of cryptography and enterprise security. Especially security in enterprise security is very important, because there you are making money. When someone is running a business, you will always sign up service level agreements. So in case if you are not able to provide proper security to some enterprise from whom you are charging money, it will become drastically difficult for you to overcome. So this becomes very sensitive. Had it been an academic area, and suppose one mail was read by one student by hacking, okay, it doesn't make a lot of difference, right? So that is a very critical area where they are working. Then, of course, Raghu is there. He is the technical leader, and works on customer delivery and engineering of security at Cisco, located at Bangalore. And he also solves, of course, obviously, most complex security challenges which Cisco's customers face. Once again, the handling customers is rather more difficult than doing research in Cisco laboratories. So this is the most challenging area where they are working. And Raghu is also part of the Cisco team developing security training content for their employees. So as a part of their Ninja program, he is the co-architect of the Security Experience Center, which is first of its kind in Cisco. So this is another good thing. And the topics which generally the areas in which he works is network security, IoT security, container security, zero trust architecture, and blockchain. in fact, I would even look forward to let Raghu explain what is a container, right? What is zero trust architecture? What IoT is, because usually they're using a Raspberry Pi or Arduino or some Node MCU or ESP32, people say I am doing IoT, right? And then they never even talk about how their protocols have been working, how vulnerable the protocols are. So insiders view as a technical leader and expert. Of course, I would look forward to make the students understand what network security is, what IoT security, what it is all about, and of course the distributed technologies of trust like blockchain. Now, blockchain is emerging area. Everyone talks about blockchain, but no one actually literally understands a blockchain, right? Especially thinking about a private chain or the public chain. How what a chain means, right? So that will be very interesting for all the participants and including the faculty members, including me. I'm also looking forward to listen to each of you the complete session. So I welcome Raghu and Nitin to please go ahead with their talks. And thank you very much for being with us. Please.
Thank you so much,
Thank you.
Mr. Professor. I think this was by far the most kindest and elaborate introduction. So hopefully we would live up to the expectations of the talk and do justice to it. So one thing that me and Nitin we always try to do is initially you might feel first few minutes of the presentation are disjoint and you might feel that it is not making sense, but have that faith for first 30 minutes and you would see that they are all very small pieces of a bigger puzzle, and towards the end of the session it would look like a solved puzzle or a worthy enough painting which we are
the way experts throw riddles, huh? The way Batman handles the riddles. Very good. Go ahead, please.
Thank you so much, Dr. Rajput. I love the fact that you mentioned riddles, because that's what today is all going to be about. We're going to be doing a lot of missions, a lot of riddles, puzzles, if you may call it. So thank you very much for having us. And I'll start sharing my screen.
Sure. So okay, please.
Are you able to see my screen now? The presentation?
Yes, we can see it.
Okay, awesome. Thank you so much, and I'm really sorry about that time that I took. I was just trying to figure out which screen I have to show. I've got multiple screens over here.
Nice.
So thank you very much, and let's get started. So today's topic is cryptography for networked communications. So we already discussed, Dr. Rajput gave a pretty heartwarming introduction to us. So that's us, me and Raghu. So we both are technical leaders at Cisco CX. Talking about myself, I joined Cisco back in 2012. And I think it's pretty safe to say that 1/3 of my life on Earth has been in cryptography. That's what I've been doing. That's what I do day in and day out. So a lot of my focus is generally on enterprise security. I work on a lot of, if you might have heard about VPNs, virtual private networks. That's what I do a lot. Sometimes people also call me a tunnel plumber, because that's what I do for the most part of my days. I fix VPN tunnels. So it's probably not wrong to maybe call me sometimes tunnel plumber in the sense of cryptography. So that's about me. So Raghu, please go ahead.
So there's one thing that me and Nitin are very passionate about: usable security. Security sounds all good when we read it in books. We make it sound complex all the while. That security is the most complex thing. You can design the world's most secure algorithm or most secure product, but if it is not usable, that would not really add much of a value. From a career perspective, I think me and Nitin have been following each other. In our first company, I joined in, I think, just 3 months prior to Nitin joined in. Then we moved to Cisco back in 2012, and it has been happily ever after. again, in the security domain, while Nitin has been focusing primarily on VPN, my focus has been on firewall, IPS, and next generation firewall. Now, what we have done is in this session on cryptography, we'll start with very basics of cryptography, and then we'll talk about usable cryptography, which is commonly known as applied cryptography. How do we apply it in things that you and me do on a daily basis? And how is it related to me, and why should I be worried about what's happening in cryptography? So with that said, feel free to ask questions throughout in the chat window too. If there are any feedback, we'll take that and quickly modify the content accordingly and answer them either on chat or for the benefit of the larger audience on the audio bridge. So
absolutely.
Let's start.
Yep, let's begin. Like Raghu said, we'll really appreciate if we can make this session interactive. That's what we're going to also try. Feel free to post any questions. And like I said earlier, we're going to have a lot of activities, missions to solve as well over here. So without any delay, let's begin. So generally, when we talk about cryptography, there are two characters which are like the most famous, right? Anyone wants to take a guess on what those two characters are when we talk about cryptography? Feel free to unmute yourself and share your answer. We'll love that. Anyone?
Yeah, I just saw a ping in the chat and it said Bob and Alice.
Oh, yes, absolutely. So it's Bob and Alice, or Alice and Bob. These two are the most famous characters when it comes to anybody who's reading about cryptography. So we thought we'll use the same characters, but let's give the story a bit of twist. Okay. So today we're going to look at this story, really. Okay. Now, this story is happening somewhere in Cryptoland. Now, what is Cryptoland? I would want you to run your imagination, right? Think about any place that you wanted to visit last year, but could not because of the COVID. And that is your Cryptoland. That's where you relax as well, right? So because you relax, you learn the most. So somewhere in Cryptoland, this story is taking place. And it's 9 p.m. in Cryptoland. So it's Cryptoland Standard Time. And the venue, the place is Alice's residence. So it's 9 p.m. Alice is happily sitting at her home watching television, and the doorbell rings. And there is a strange man at the door. Now, Alice opens his door, and the man says, "Fate whispers to the warrior." That's a bit odd. But Alice replies back, "A storm is coming." To which the man replies, and the warrior whispers back, and Alice says, "I am the storm." When Alice says, "I am the storm," the man hands over the book that he's holding and gives it to Alice. Now, what do you think happened over here? What these two folks, Alice and this strange man, were doing, and then the man handed over that book to Alice. What do you think happened over here? Anybody wants to take a guess? Anyone?
Okay, there's one thing which says there's a secret message in the book, or a secret message. Something important was supposed to be delivered, and I think we got the right answer.
Okay.
Which is a combination of all the pings that came in. So I'll just summarize. There was a secret message to be shared between the strange-looking character and Alice, which is the right thing. When we want to share something which is so secret and important, we have to use either a coded language, either we have to exchange something before we hand over the book. So the two important technical words which are relevant here is some sort of key exchange happened.
Correct.
Or some code exchange happened, after which the strange looking character, handed over the book to Alice. Now, there's another answer that came in is sharing of public key to the receiver, which is also the right answer, but at this point in time, we'll go very step by step. So right now, we'll hold on to that thought of public key. Right now, we are looking at basically some sort of key exchange that happened and the strange looking character handed over the book to Alice.
Exactly. So once this is done, Alice takes that book and opens that. Now inside there's a pen drive. Okay. Now she goes back and plugs that pen drive to her system and hits the play button. And up comes Mr. Bob. So Bob, who is a secretary at SIA. Now what is SIA, Raghu?
SIA. Remember we started with an imaginary land called Cryptoland. Mm-hmm. Now, as does every nation has its own intelligence agency, Cryptoland also has its own security intelligence agency. And what they do as part of that is, because it's an imaginary land, they work purely on technical aspects and use of technology in order to encode and decode messages, crack secrets, find culprits, etc. They don't really have the traditional way of finding out anomalies around. So that is SIA, where Bob and Alice are both employees of.
Got it. Yep. Awesome. Thank you. So up comes Bob when she hits the play button. And Raghu just told you who Bob is. He's the secretary at SIA. And Bob says, "Good evening, Miss Alice. This is Mallory. She runs a syndicate of covert operators, and they continue to wreak havoc around the globe. Of lately, they have started something which is called as TAS, which is Terror as a Service. Now, they've tried for long to hunt Mallory, but not yet successful. So far, they do not have any information about Mallory. Now, your job, if you choose to accept it, is to infiltrate Mallory's gang and extract information. At any point, if Mallory or anybody in the gang comes to know about Alice's job, that she works for SIA, Bob will disavow any knowledge about Alice. Now, good luck. And this message will self-destruct in 5 seconds. And zap. The message just got destructed. So what do you think is happening over here? What do you think Alice does for a living? Who is Alice? Anyone?
Modified spectrum. Modified.
I could not catch that. Could you please repeat? Raghu, can you hear her?
I could hear her very, very faintly.
Yeah.
But in the meanwhile, there are few things that came up, which is 008, Grey Hacker, Secret Agent,
okay,
etc.
Nice. So that's what we really wanted to do. Essentially, like I said, give the story a bit of a twist and add colors to their characters. So in this specific case, the story that we're going to look at today, Alice is a special agent and Bob is the secretary at SIA. Now, can you relate to this discussion, what just happened, to any movie specifically? Any movie you might have seen?
So the reason we asked that question is because throughout the discussion now, it would be references to movies, web series that you would have seen, because cryptography is a very complex subject. unless and until we understand it with examples and things we do, it would be a little tricky. So I see that people have reference to Johnny English, which we never thought might be the answer. So there's Johnny English, there's Mission Impossible, there is Men in Black.
Nice. Yep. So what me and Raghu had in mind while creating this was Mission Impossible. But Johnny English is a good addition, really. Thank you very much for that. So let's go ahead. So for being successful in her mission, Alice would have to do a series of missions like we discussed earlier. And what she will need to be successful in these missions is her crypto knowledge. So what we are going to do today as a group is help Alice solve those missions. Okay. And we're going to look at what crypto mechanisms Alice must know so that she's able to safely and securely exchange or rather send information from Mallory's gang to wherever she lives, somewhere in Cryptoland, back to Bob, who is sitting comfortably in SIA offices. So let's begin. Now, before we dive into cryptographic mechanisms and look at them, let's do a very quick exercise. Let's start by breaking some code. Now, here's some gibberish, some ciphertext. Okay, we've used some way of encrypting it, maybe hashing it. We don't know yet, right? We don't know what a hash is yet as of now. But we just wanted to start off by this, right? So here's some ciphertext, and let's see who can break this code. And trust me, if you're able to set the context with what we just discussed, it should be easier. So if anyone finds this code, just shout out Eureka, okay? And share the code, share the message essentially, not the code. So I'll probably give 5 minutes and it could be a nice activity. If anybody is able to break this code, just shout out Eureka.
Yeah. If you're able to break it now, great. If not,
yes,
you can take the screenshot of the message that you see on the screen, and as Alice goes over her journey of understanding cryptography and how they are used in real-time system, you can then again give it an attempt in order to crack it back.
Yeah. So we'll maybe wait for a few minutes before we proceed forward.
Okay, no luck yet.
Okay.
So we can.
Problem. Yeah, that's okay. If you're not able to break it as of now, that's perfectly fine. Like Raghu said, do take a screenshot, and so that you have a record of this. And as we proceed forward, you surely will be able to break it very easily. Okay, then I'll move forward then. So let's kickstart by looking at the different cryptographic mechanisms. So Raghu, I'll hand it over to you.
Yeah. So what we will do right now is we will break the entire cryptography into the basic building blocks that used together form our cryptographic algorithms, our cryptographic systems. So let's look at what are these basic building blocks of cryptography. Now, for those who are more from a programming background, think of this as what are the basic keywords, what are the basic constructs that are available in a programming language using which you can build something or develop something in that programming language. So we will do the same thing with cryptographic mechanism. Now, the entire cryptography can be broken down into 6 basic building blocks. The first block is encryption. What is encryption? Now, encryption is a mechanism by which a sender of a message can send it to the receiver without anybody in between knowing what that message is, so that the intended receiver of the message is actually the right one to get the message. I'll take a simple example. Now, if I were to talk in a language which is known only to me and Nitin on this call, that would be an encryption that me and Nitin are using in order to communicate, while everybody on the call has no clue about what is being exchanged. So that is encryption. The second part is data authentication. Now, what is data authentication? Data authentication is as simple as, did Nitin receive the exact same message that I sent, or there was somebody in between, popularly known as eavesdropper, who modified the message and then sent it to the receiver. What this does is, the message that I had planned to send is modified in transit, which means Nitin is now not getting the true message that I had sent. Now, in case of computer systems that use cryptography and exchange messages or communicate with each other, it might be IoT, it might be sensor-based network, it might be a communication between two computers, phones, etc. The authenticity of the data is most important part, and hence data authentication is the second building block of cryptography. The third one being key establishment. We did see a small reference to what key establishment was, where, remember, the strange looking character said a string of words. The receiver, which was Alice, she also replied back with a specific string of words, and then they established that they are the right parties to receive the message and then handed over the book to her. So key establishment becomes a very crucial part, because we are communicating with people who are at a large physical distance, maybe on the other side of the planet, while we communicate with them. So having a robust mechanism for establishing the key before the message is sent is very crucial. Then comes signatures. Parallel analogy to signatures is what we say as self-attestation. Self-attestation means the person who is signing the document, has validated the content of the document, and I hereby say that I'm signing this. That exactly is the same behavior in case of computer-based communication system. The sender of the message has to validate that it is indeed him who is sending the message, and that is achieved through signatures, also known as digital signatures. Then comes a very interesting concept of random number generation, because as per my opinion, the strength of entire cryptography is based on random number generation. Now, over the next couple of hours, we will see why random number generation is just not a random step in cryptography, but indeed the most important step or building block of cryptographic algorithms and cryptographic systems. So that's with random number generation. And lastly is my favorite part of cryptography, which is hashing. We'll look into what hashing is now in detail. So these are basic building blocks. Now, while we go into hashing, Nitin, I did say 2 eureka moments. That means we have Ritika and Badawat, if I'm pronouncing it wrong. Sorry for the wrong pronunciation, who have found what the answer is. So if you can just ping it on the group, that would be
so may I say it like...
Yeah, sure.
Go ahead, absolutely.
Yeah,
Just say Eureka and then go ahead.
Cryptoland.
Can you go again?
Alice and Bob in Cryptoland.
Exactly.
Okay, and the other person who cracked it, did you get the same message or a different one?
Yes, sir, I got the same message.
Perfect. We will look into what actually happened and how they were able to get the actual message. But the message at this point in time was Alice and Bob in Cryptoland.
Yep.
Now, what was done to the message? How were they able to recover it? Is what we will go through as part of this journey. But first thing first, hashes. Hashes and Hmac will now dissect into what are hashes and what are Hmac and why are they so important part of cryptographic systems. So let's look at what hashes are. And we start with a very interesting image on the presentation, right? I believe most of you, if not all, would have either seen this very popular web series or would have heard about it when our friends and colleagues constantly keep talking about it. Now let's look at a very simple reference here. You are watching season 6 of this cult series called Game of Thrones. Now, unluckily, you have not seen any of the previous seasons. Meaning, when season 6 starts, you have no clue what has happened in the previous season, which has led to whatever you see on season 6. The question is, if we are in such a situation where we see something, but based on that, we are not able to track back what would have happened in season 1, right? It's very difficult. We can't really tell, at least for the ones who have seen this series, it is very, very difficult to tell, looking at a particular season, what has happened in the previous season if you have not watched it. Similarly, a small change in one of the previous seasons would have ensured that there is a huge difference in the current season that you're watching. Meaning, if some change happens in the past, in the series, the current situation would completely be different. Now, why are we talking about this season and this particular example? Because this is what hashing is all about. A small change in the input should result in completely different output. While if I see the output, I should not be able to find out what the input was. So this is a very simple analogy of what hashing is. Now, while we understood the analogy of the hashing, let's look at it in technical terms on what are hashing algorithms and what are these attributes of hashing algorithms. So if you look at the screen, there is a message that we have to send, and this message can be of any length. It can just be a message which says hi, or it can be a message which is of size 10 GB. But whenever the message is sent through a hash function, the first mandatory property of the hash function is it should always generate a fixed length output. Meaning, even if it is a small message, a message which is bigger in size, or it is spread across multiple pages, I should always generate a fixed length output. This property is important because it makes it very complex for an intruder to look at a hash and determine what the input message was. The second one is, which is what we saw through the reference of the series, which is avalanche effect, meaning a small change in input should make the output completely different, thereby making it robust against few of the known attacks in cryptography. We will look into what those attacks are also. So all in all, avalanche effect is a small change in input should ensure that the output is completely different. The third one being pre-image resistance, meaning no two messages should generate the same hash, because if two messages generate the same hash, it would lead to all the cryptographic systems that we are using to fail. Now, at this point in time, you might feel that what's the big deal if two input two different input messages generate the same hash. We will look into application of hashing in subsequent slides, and then you'll realize how important it is for a hashing algorithm to ensure that there is no collision or there is no pre-image resistance where two messages will generate the same hashed output. Now, with these set as the properties of the hash, there is also one thing that becomes very crucial when we build systems that leverage hash is the performance. While the first two properties should be very easy to calculate and they should be able to compute faster, the next two properties, which are pre-image resistance and collision resistance, from an attacking perspective or from an attacker's perspective, they should be equally hard to break. So when we design systems, the generation of hash should be faster, while breaking the hash should be equally difficult. With that said, let's look at something interesting now. What are our existing hashing algorithms and how much size of input do they take and what is the size of output that they generate?
Sure. Raghu, just before that, I think I'd just like to add, like Raghu mentioned, right? And not just hashing. Actually, if I talk about majority of the cryptographic algorithms, there's always going to be one operation which is going to be easy. And then there's going to be a reverse operation, which is going to be extremely difficult. And that is what really determines the strength of that algorithm. Like in this case, it should be extremely easy to calculate the digest or the hash of a message, but then it should be extremely difficult to go the reverse way, which is you have a digest at your hand, but then to identify the original message from that, this should be extremely difficult. And that is what defines the strength of an algorithm. Now, having said that, Raghu, do you want to take them through how a hash is calculated through the Merkle-Damgard?
Oh, yeah, sure. So we'll now go into the practical aspect of it. There's a data that for which I have to generate the hash for. So what does the system do? Now, with the data, I divide my entire data into blocks. Now, there's a reason why we divide the entire data into blocks, because the underlying system cannot really transmit a 10 GB of data or 100 GB of data. It always calculates and transmits it in terms of blocks. So the step one is I divide the entire input message into blocks of equal size. When we say we are dividing given input data into blocks of equal size, we'll run into a situation where there might be a block which is of a smaller size. In that case, we use what is called as padding, which is filling out the remaining spots with zeros and ones. Now, when we add that pad, what we get is equal size block. What is the next step? The next step is something called as IV. IV stands for initialization vector. At this point in time, let's think of IV as a random string of message, which is taken as my first block that will be used in conjunction with the data that is divided into blocks. Now, you will also, some of you might think of, have heard of initialization vector being used somewhere else too. Again, hold on to that thought. That is one of the applications of hashing in real-time scenario. Now, what we do with the IV or initialization vector? We take the initialization vector, hash it, a particular mathematical function basically, with the first block, and that generates an output. Now, the output that is generated by performing the mathematical function on the initialization vector and block 1 suddenly becomes the initialization vector to block 2. The output generated on block 2 is then taken to block 3 and so on till the end of nth block. Now, what do we get at nth block is the hash of the entire data. Now, this hashing output that we see is a result of the hash computation of the input data along with initialization vector in a step-by-step procedure which has got us a particular value. Now, from a computation perspective, this computation is super fast. While it looks to be n steps, it really happens before you can, blink your eye. So this is what Merkle-Damgard construction is for generating the hash. This is something that is really being used in the applications that you and me use daily. We will look into what those applications are.
Thank you. So, having said that, I think, Raghu, let's talk about some of the different algorithms that we have for hashing, right? So, this table is essentially a rough comparison of the different algorithms that you might have come across, like MD5 or SHA-1. And then there's a family of hashes which is called as SHA-2, which includes SHA-256, SHA-384, and SHA-5 and 2. One thing to note is, if you notice, the output size is increasing as we move from MD5 to SHA-1 and then to the SHA-2 family. And then the other thing is the maximum message size that this algorithm can handle. Sorry. Okay, I think that was just someone. Okay, no worries. The other thing is the maximum message size. If you see, even that is increasing, and that's the maximum message that this algorithm can possibly handle, and above which the probability of having a collision increases. And then we have the last column, which is the collisions found, right? So if you see MD5, we have said the collisions found is yes. So it is not safe for anybody to use MD5 as a hashing algorithm because we have already found collisions with that. Now, the next thing is SHA-1. And if you see, we mentioned that the collision found is yes, but it's hard. So let's first look at collisions. Like, what do we mean by collisions? Like Raghu mentioned earlier, if you can have two messages which are different messages, pass that through a same hash function and get the same digest value, that is when we call a collision has happened. And the way it happened with SHA-1, it's called Shattered. Anybody who's interested, do go through the link over here. That's shattered.io. So let's do this. Let me show you a very quick demo on this one. So I'm just going to stop the slideshow and let's do this.
So while Nitin brings that up, right, for folks who are working on apps, building apps, where you would use hashing, rule number one is do not use MD5 as a hashing mechanism because MD5 has already been cracked. In a way, there are collisions found. So when you build systems which are communicating, do not use MD5 and if possible SHA-1 also, where there is a need to perform data authenticity. So what Nitin is going to show here is how SHA-1 had collision.
Yep, thank you, Raghu. So right now what I have done is I have opened two pictures. One is Mars.jpg, the other one is Venus.jpg. And as it's very clear, these are two very different images having different contents. So the way we calculate hash, let me increase the font size, is by doing OpenSSL and then write the algorithm that you want to use. So in this case, I want to use the SHA-1 algorithm. So I'll say SHA-1 and then let me put the file name. So it's mars.jpg. Okay, I get this hash value. Now I'll go and say OpenSSL SHA-1 Venus.jpg. And as expected, these are two different images and the hash value of these two images is different. So far, so good. Nothing surprising and nothing out of the box. Now let's do this. Let me run a script. Okay. What this does is it creates two more files which are called as marscollision.pdf and venuscollision.pdf. So let me open that. So this is Mars collision. And this is Venus collision. Okay. So again, two different files having different contents. But let's do this. OpenSSL, SHA-1. Sorry. Mars collision and OpenSSL, SHA-1. Venus collision. And voila. We see something really odd over here, right? These two files, Mars collision and Venus collision, which are right over here, are different. But the SHA-1 hash or digest of these two different files is same. And this is what we call as collision, wherein two messages, which are different messages, eventually run through a SHA or a hash function, and the digest comes out to be same. And that is called as collision. So what we just saw is SHA-1 is prone to collision. And if you want to read up on how I did this, do go on that link, that shattered.io, and I'm sure you'll find it very interesting. At the same time, if you see, it doesn't really break SHA-256.
Yeah, I was about to bring up that point. So if you use SHA-256 instead of SHA-1 here, we wouldn't have seen the collision. Presence of collision just means that the algorithm has violated one of the prerequisite condition for a hashing algorithm. The moment you find a collision, that particular hashing algorithm is no longer safe to be used in the applications that we develop or the communication channels that we set up.
Exactly. The other point I want to highlight over here is, like we talked about, the output size. So if you see over here, that's the SHA-1 output, and this is SHA-256. SHA-256 output is definitely longer compared to SHA-1. Now with this, let's go back. Okay. Okay, so Raghu, do you want to take ahead and talk about hashing?
Okay, now based on what we saw and what Nitin exactly did, the only difference here being in the demo, we had an image file. But what happens when we are surfing internet, trying to communicate to our friends, etc., is we have the message that we need to transmit. We compute the hash of the message, and we transmit both the message as well as the hash appended to it. Now, when Alice sent that message across and Bob received the message, what Bob does is, in order to ensure that the message is not tampered in between or modified in between, he computes the hash again. And then he checks the hash that he has computed with the hash that Alice appended to it. And if they are equal, Bob says that the message is valid and no tampering of the message was done. However, if the hashes don't match, then somebody in between has tampered the message, meaning the authenticity of the message is lost. It can be a change of message as simple as to annoy or for the sake of fun, to as grave as a change of password, a change of content of the message, which just transfers a property that Nitin has brought on his name to my name. So this is what a small property of collision in the hashing algorithm, if violated, can lead to. So this is the basic premise around hashing.
Yep. So like Raghu said, traditionally, if you have to use hashing, when we're sending a message M, we will send the hash along with that, and then that can be used to do comparative analysis and essentially recompute the hash on the receiving end. If it matches with the hash that was sent, the message is fine, was not tampered with. Otherwise, somebody did play with that message in transit. The other scheme, apart from just the regular use of hash, is called as Hmac, okay, which is hashed message authentication key. Now, what happens in case of a Hmac is when Alice has a message to be sent to Bob, before that, Alice and Bob do some kind of key exchange, and they already have a pre-shared key K shared amongst them. Okay. Now,
I think Nitin might be having a power outage. So while he joins in back, let's discuss about Hashmac that Nitin was covering. The inherent problem with hashing was we always knew that there's a message and a hash calculated. Now for an attacker, in order for him to know what is the hashing algorithm that both Alice and Bob are using, what he needs to do is he needs to send a message of his own to see what hashing algorithm that they're using. Now, in order to do that, or in order to avoid that particular concern, we came up with what we call as Hmacs. In case of Hmac, in addition to just the hashing function, there is a key that is being appended to it. Now, while the key is pre-shared, what we do is, instead of just hashing the message, we hash the message appended with the key. So even if there is somebody as an intruder in the network who gets or captures the message, he will not be able to get the key which Alice and Bob have shared beforehand. So the presence of a pre-shared key that is exchanged between Alice and Bob ensures that the hashing algorithm or the hashing mechanism is little more stronger than just leveraging plain hash. This is called as Hmac. You might have heard Hmac being also referenced to as salted hashes. So when you hear the word salted hash, it is identical and same as Hmac. We'll just wait for quick 15-20 seconds for Nitin to share the screen back.
Hey, I'm back. Thank you. So, really sorry, I just had a power problem. So let me just try and share my screen. I'm just trying to see which one is being shared.
So I just discussed about what Hmac is and what is the significance of the key that is pre-shared. Sure. It makes it a little more difficult for an intruder to determine what hashing algorithm was being used.
Yep, true. Thank you very much. So because the intruder would not really know the pre-shared key that was there. So having said that, now that we have quickly looked at the use of hashing and Hmac, let's come to the first mission. And the mission is Alice got access to a very important file, and this file must be sent over to Bob. Now, Alice must ensure that when Bob gets it, he is able to ensure that the file was not tampered with. So far, Alice's crypto knowledge is limited to hashing and Hmac. So what do you think Alice should use? Should she use hashing or should she use Hmac? What do you think? Help out, Alice. Anybody wants to take a guess?
Okay, I saw one answer coming in as Hmac. Hmac, and most of them are Hmac.
Nice. Okay, so let's very quickly go through that. In case there is somebody sitting in the middle, which is man in the middle, in this case Mallory. Let's say if Alice had a message to be sent to Bob, she sends the hash H and the message M. Let's say Alice is trying to send a message that I found the address of Mallory and here's the address. Okay. Well, Mallory intercepts this message, which is M, and changes that. Says, nothing yet found for Mallory, don't know anything about her. Now, what she does is she changes this message M and also then recomputes the hash. Okay. She recomputes the hash on this changed message, and this is what is eventually sent to Bob, which is the hash recomputed and the message which has been changed. When Bob gets this, he calculates or computes the hash over this message, which is nothing found yet on Mallory, and tries to match it or compare it to the hash which was sent, in this case, not sent by Alice, but by Mallory. And he gets it and he says, you know what, so far nothing has been found. Whereas what Alice really meant to send was, here's the address of Mallory. Okay, so that is why using a plain hash might not be a good option over here, because an attacker could recompute the hash along with and change the message and send that over. And that is where Hmac would come handy. The reason primarily being, when Alice has to send out the message, along with that, she sends the Hmac over here. Hmac is nothing but you concatenate the message with the pre-shared key. Okay, and over that, you calculate the hash.
So there's a interesting question, and I think that deserves to be answered online, is how can Mallory recompute the hash as she does not know what hashing algorithm Alice had used when she was sending the message to Bob?
Okay. Somebody had a question? So, if I have to go back on the question that Raghu just asked, right? If you look over here, the message M and the hash is being sent in clear text. So I already have the message. Okay. What I can essentially do is run this message through the known hashing algorithms. So let's say starting from MD5 to SHA-512. And I can then see which algorithm leads to this hash value or the digest value. And then that's where I see this is the hash algorithm which Alice is using.
Just to append to that, right? The number of hashing algorithms that are available, they are limited. It's not that we have infinite number of hashing algorithms. In this case, even a brute force would take less than a couple of seconds to determine which hashing algorithm generates the same hash as that of what Alice had computed when she was sending the message.
Yep. Hopefully that answers your question.
And interestingly, right, for everybody's benefit, remember the message is sent as it was being sent earlier. Hash is not changing the message. It is not encrypting the message. It is not translating the message. That's another thing to note, why hashing, a plain hash, is relatively insecure as compared to Hmac.
Correct. So with Hmac, like I said earlier, we typically as an input, we take into account the message M that has to be shared, and along with that, the pre-shared key. And we do not send the hash, rather we send the Hmac in this case. When Bob gets it, only he and Alice knows that key. So he takes that message, appends the message with the key that is only known to them, and then calculates the hash on that. And then if it matches, that means the message was not altered in the transit. The beauty about this is Mallory would not know the pre-shared key K. And the drawback about this is we have to ensure that Mallory doesn't know the pre-shared key K. There has to be some kind of secured exchange of this pre-shared key K before they can really send the data out. So the beauty and the drawback is the beauty being only they know the pre-shared key. So Mallory cannot know that. So they can evaluate if the message was tampered with or not. The drawback being you need to figure out some kind of secure key exchange. Maybe before Mallory or maybe before Alice was being sent to infiltrate Mallory's gang, they shared some pre-shared key with her. So that is what Hmac does. It's essentially adding a pre-shared key so that you can easily figure out if the message is being tampered with in the middle or not. So I'll stop for a minute, and if you have any questions, feel free to post your queries. Raghu, any questions as of now?
None on the chat yet.
Okay.
Or should we ask a question?
I think we will, but that's maybe after applied hashing.
Okay.
So now that we talked a bit about a theory, right, of what hashing is, how can you use hash algorithms, what is Hmac, and where Hmac is used, let's talk a bit about the practical implementation of hashes. Where do we see hashes being used in the industry? And that is what we like to call as applied hashing. So with that, Raghu, do you want to go ahead?
Yeah, so we did speak about hashing is so important, etc. But we did not look at real-time applications that uses hashes. So now there are three major scenarios where we are using hashing in practical application. Now let the last one be with a question mark, because that is something for you guys to think on where else hashing can be used. The first mechanism where hashing is used is in passwords. What do I mean by hashing being used in passwords? Whenever we enter password, whenever we store password, a good cryptographic system should never store the password in clear text. It should always store the password in a hashed form. This ensures, one, the security of the system, and two, the validation and verification now is just done based on hash, because hash of a given input string is always unique. That way, in a large database, it becomes faster for searching too. So that's one of the mechanism or real-time application where hashes are used. The second one being malware detection or malware analysis. Let's take a look at the example of that small piece of software which is present in our phones, which is present in our laptop, which we call as antivirus, anti-malware, or anti-X. How does it identify a good file versus bad file, a good program versus a bad program, a good executable versus bad executable? It cannot really expand the entire file. If I have downloaded, say, for example, 10 GB of file, the anti-X software doesn't really look at every bit in a 10 GB file to determine if it is a bad file or not. And because this has to happen in real time, they leverage what we call as static hashes. Static hashes are basically computed on all the files that are seen by on the internet, right? This is the process. There's a file, input file. a hash is generated of that file, and then when you download a new file on the system, the antivirus or anti-malware solution computes the hash of the downloaded file and checks it with its own database. If it finds a match in the database, it says that this is a bad file and deletes it. So we have actually blocked a piece of malware, a piece of bad file, without looking into the content of the file, but still doing the right thing. That always triggered a thought in my mind. We all, at some point in our lifetime, have had French fries from McDonald's. No matter which McDonald's you visit, the taste of the French fries always remains the same. This is an analogy to what we call it as hashing function. No matter what the input is, it is, if a hash function is applied, it will generate the same hash. Location where hash is being calculated, location from where the hash is being generated, timestamp of when the hash is being generated, they don't influence the output of the hash function. A given input will always generate the same hashed output. That is why hashes are extensively used in malware detection, because known bad file will always be a known bad file. So I can just compute the hash and then determine if the hash matches with a known bad file. If it matches, I'll block it. If it does not, then I'll allow the file to be installed on my laptop or a cell phone or any computational device. Ranges from a desktop computer to as small as a sensor. This is how we validate the disposition of a file without actually reading the entire file bit by bit. And then if we can go back to the previous slide one. The other one, right, is verification. Verification is when I download a software from internet. Now there are so many devices in between in the network from my laptop towards the server from where I'm actually downloading the file. If somebody tampers it in between, I'll not be able to execute the file on my laptop. Now I assume you might have faced this issue that you downloaded a file but it got corrupt. The thing that we say is it got corrupted. What we mean when we say it got corrupted is somebody tampered it. And the way to ensure that if the message or the file or the software that we have downloaded is not corrupted is through verification of the hash. So anybody who publishes a file displays the hash associated with that particular file. And then when you download it, after you download, you can compute the same hash. If the hash is matched, then the software that you have downloaded is not corrupted. If it does not match, then it is corrupted in transit. So this is what we mean by verification. Now, as a research area, right, or for those folks on the call who are interested in pursuing research as a career, you might want to read about what we call as rolling hash. And that is what Nitin will show up on the screen. For these, we call it as a rolling hash algorithm. Now, this is an area of field which makes every antivirus, anti-malware company unique. It depends upon what is the rolling hash algorithm that is being used here. Now, it's a very complex topic to be covered as part of this. So we have given the reference link to what rolling hash algorithms are and how they are very useful in case of security systems.
Thank you.
There was a question too. Does Hmacking means encrypting a message?
Okay. So the way I'll say it is it's not same as encryption. I'll rather defer it to the point where I cover encryption later on in the slides. And I think it will become very clear, but the answer would be no, Hmac is not similar as encryption. It will become more clear once we do encryption, actually. Hello, can you hear me? Raghu?
I can hear you, Nitin.
Okay, awesome. Thank you. So let's proceed.
Oh yeah, I think I see a ping from Naveen which said that answered the question.
Okay, thank you. So with this, we come on to the second mission, and to me it looks very interesting. Alice, while she was there at Mallory's place, she found a secret door, and which is locked by a digital code. Somehow, she manages to find the algorithm which is used to generate that digital code. Okay, the algorithm is you start with the string Mallory rules crypto land, okay, and then there's a numeric value that's appended to this, which is over here percentage %n. So the way the algorithm works is Mallory rules crypto land. You start with 0, okay, and you find the digest of this using SHA-256. Once you get the digest value or the output of running the string, which is Mallory rules crypto line 0 through SHA-256, you look at the first 4 characters and check if it is all zeros. So if it's 0, 0, 0, 0. If not, you increment the value of n. So it becomes Mallory rules crypto land 1. And then you again check the first 4 characters of the digest. If it's all 0, then n is the code to unlock that door. Okay. If it's not, you increment n again. So it's 3, 4, 5. So that is what you have to do. You have to figure out the value of n, because that value of n is the key to unlock this door. And Alice really has to do that, because inside that door lies some of the Mallory's secrets. So Alice would need your help over here. Help Alice find that digital code. As an example, you can, if you use Python, you can import the library hashlib. And I've just given a very brief example. So you can run it through SHA-256 like this with, let's say, 0. Look at the first 4 characters. They are not 0. So increment it. So now it becomes Mallory rules crypto land 1. And then you do it for 2, 3, 4, and 5 till the time the value of n for which the first 4 characters of the digest are all zeros. Your time starts now. Alice really needs your help. Help her identify the code to. Hey, Raghu, can you hear me?
Yeah, I can hear you. I was just trying to understand if people are actually trying to take a shot at solving the problem. Because once you solve this mission, there's something very interesting you'll realize on why we had this mission in place and how is it even related to practical systems that are being used currently.
So can you share the screen?
Yeah, just one quick second and it would be back up. Yeah.
Can you see the screen now? Raghu, you're able to see the screen now, right?
Yes, sir.
Okay.
Yes, sir, we are able.
Thank you. Raghu, anyone managed to solve this yet?
Just tracking chat. Not yet.
Okay, the same rules apply. Just shout out Eureka and you can share the code. Alice is keen to hear what the answer is.
So let me make an attempt to break down the problem. So Nitin, if you can go back to the previous slide,
Sure.
maybe that would help. So the scenario is the string is Mallory rules cryptoland, followed by an integer. Now, when we append that integer and calculate the SHA-256 associated with it, we get a hash value. Now, the only condition for the lock to be opened is the first 4 characters of the hash should begin with 0. Now, the sample code that Nitin shared that just speaks about how do you calculate the hex digest if you are using Python. Now, you can use C as a programming language, Go, whichever you feel comfortable. The only criteria is Mallory rules cryptoland should be appended with a numeric value such that the hash generated should begin with first 4 zeros.
And the hash algorithm should be SHA-256.
Yeah, the hash algorithm should be SHA-256. So we'll give it another, say, minute or so, Nitin.
Sure.
And when the reveal happens, right, why we did this activity, you would be able, you will be appreciative of the fact that why this is such a crucial mission as part of the session. I did not get the solution, but I saw a ping from Hitesh, which said first 4 bits should be 0 is application of blockchain, which is right, with the only difference that it is not first 4 bits. As of last week of February, it was first 30 bits to be 0. Now, the computational challenge that you guys are facing here, imagine the same multiplied to a factor of 30 times. Now, if you are spending so much time in order to get a hash where the first 4 bits should be 0, imagine the computational overhead and the computational challenge that exists when the hashing algorithms are used in blockchain, because the requirement there is first 30 bits should be 0.
Exactly. And that is called the proof of mining algorithms. Okay. They are bound, like Raghu said, they are bound to be computationally intensive. They are bound to be memory intensive. Okay. They are bound to take a lot of compute power. And as of now, it's 30 zeros that you have to identify. We'll actually see where and what really forms the input of that. But you're correct. They are used in blockchain proof of mining. So having said that, let's break this problem down now. Okay. Anybody wants to take a jibe at this? What is the value, or how can you unlock the door? Anybody wants to take a guess? Or maybe can someone share their approach, what they have been using?
Sir, hello.
Yes.
So what I did was I just used a for loop in the range of 0 to 1 million, and I was like getting the hash of every number, like Mary rules cryptoland 0, 1, 2, and if the 4-digit matches 0, 0, 0, then like it will just print the ith number and break out of the loop.
Okay. And were you able to execute this program?
Yes, sir. Like up to 1 million, I didn't get any.
Ooh, okay. I would recommend check the program once. But let's do this.
I think your conditional matching
Correct.
statement might be having a small bug. So what we'll do is now, just in the interest of time, we will show a sample code and the corresponding value.
So here's a small program that I wrote. Okay, I just used just like you, right? I just used a large value. I start with the base string of Mallory rules crypto land, and I compute the digest on that using SHA-256. If the first four are 0000, I go ahead, print the value and break the loop. So let's do this now. Okay, so let's do this. And this should be this one. Let's do this. So the answer is 74164. So at 74164 is when the first four characters are all 0. And so that means that the key to unlock that door that Alice had to punch in is 74164. Make sense to everybody?
Yes, sir.
Thank you. So, like we were discussing, this really forms the basis of blockchain, proof of work mining algorithms. Having said that, because we're on the topic of blockchain, let's take a lighter moment. Okay, why is blockchain important? Back in 2017, I guess, there's this company which added the word blockchain to its name. Didn't really implement blockchain in what they were doing, just added the word blockchain to their name. And their shares or the stock prices, they saw a price surge by almost 400%. Now that's the power of blockchain, right? You add the word to the name and your stocks go 400% up. And similarly, very surprising, Long Island Iced Tea Company, okay, even their stocks rose immensely high, about 300% if I remember correctly, by renaming themselves to Long Blockchain. Okay, so that's the hype about blockchain. You change your name to include blockchain, and the stocks were going up. So what is blockchain, right? And how are hashes, what we just discussed, used in blockchains? So that's the general idea of blockchains. We start with something which is called as a genesis block, the first block. Okay. If you see over here, the hash of previous block, the field over here, is marked as none because that's the first block. As we start doing transactions, as we start adding more records, what we do is we create the block number 2. Okay. In block number 2, in the field of hash of previous block, we put the hash of genesis block. Okay. Now, the thing over here that you have to do is you have to select a value of nonce, which is over here, which is similar to the value of n that we calculated in the previous exercise of the mission. Okay. The idea is to identify the value of nonce such that the hash of this block, which is block number 2, comes out with leading 30 zeros, as we said. So we were looking at first 4 zeros. Now you have to look at first 30 zeros. Okay. Any miner who's able to identify that value of nonce such that the hash of block number 2 has leading 30 zeros, he gets the reward, that miner. Okay. And now we feed the hash of block number 2 as the hash of previous block in block number 3. So if you see over here, we have different blocks, 1, 2, 3, 4, and all of them are being linked to each other through the hash of previous block field. At the end, let's say if somebody changes some value in the payload of block number 2, okay, and we are currently, let's say, at block number 79. For them to ensure that it doesn't get caught, they'll have to recompute the hashes from block number 2 to 79, which is a huge task. Okay, and that's why we say the blocks are immutable. Once they are there, they are formed, they are created. It's very difficult for somebody to go back and change some transaction, something in the payload in one of the previous blocks. So we essentially are creating a chain of blocks using the hashes. And that is a very like a 10,000 feet view of how and what blockchains work. Raghu, do you want to add anything?
Okay, sorry, I was speaking on mute. So what I want to add is a bit of security aspect to this, right? If you are someone who follows what happens in security domain, you will see a stark dip in the number of ransomware attacks that have happened. Because ransomware is one-time reward for the attacker. I compromise somebody's system, I encrypt it, I take some money or Bitcoin to give them the key to decrypt it. This is one-time reward for a lot of effort to compromise somebody's machine. What blockchain and crypto mining has brought onto the table is what we say as compromise endpoint, but rather than encrypting their resources, we will leverage their compute resources so that I can use that compute resource in calculating hashes and validating the hashes as part of crypto mining. Now, if we go back to the example that we had, right, just calculating a hash which starts with 4 bits of 0 took certain amount of time, and this has to be done across all the blocks with the first 30 bits as 0, and this only keeps increasing. It makes the entire process very CPU intensive, and hence the dip in the ransomware corresponds to the fact that now attackers are trying to leverage our compute resources as compared to trying to infect us with a ransomware and getting a one-time reward for it.
Yep. Thank you for that, Raghu. Having said that, this brings us to a very interesting point. Okay, I think now that we're almost at the end, the logical end of hashing, I think it's worth brainstorming on one specific topic. What we just discussed about hashing is you feed any input to a hash algorithm and it gives you a fixed size output, right? Maybe a 128-bit output. What that means really is you can have a 1 gig file as an input and you feed that to a hash algorithm and it gives you a 128-bit output, right? You feed a 2 gig file to that, you get a 128-bit output. So irrespective of what input size you are feeding to a hash algorithm, you're always getting a fixed size output. Doesn't that seem very similar to compression? Don't you think with this, what we just discussed, hashes can possibly be the world's best compression algorithms? What do you think? If yes, I think it's very clear. If yes, why? But if you don't think so, if you don't think hashes can possibly be sought after as the best compression algorithms, why do you think so? Anybody wants to take a guess on that? What do you think? Anyone?
I see one ping as collision. And the other one is interesting. It says issues with decompression.
Can you elaborate on that? Like when you say issue with decompression? You can unmute yourself and also share with us. Well, you're on the right track. Who did we get any new answers?
I see one, it says loss of information while trying to decompress or to generate 2 GB file from 128 characters. They are on the same line. I mean, the thought process is right, but...
Exactly. So let's discuss on this, right? When we were discussing about the properties of a hash function, we discussed that there will be one operation that is going to be easy, which is creating a digest from a given input. So input can be any size. Computing the hash on that input should be very easy. At the same time, though, ideally, it should be extremely, extremely difficult to go back from the digest to the original message. So what that means really is, if you want to use hashes as maybe compression algorithms, it'll be extremely easy for you to compress in this term or in this context to compress, let's say, a 1 gig file into a 128-bit digest output. But then it should absolutely be impossible, very difficult mathematically as well, to go back from that 128-bit digest output to the 1 gig file. And that is why, like you likely said, decompression is a big problem. So you cannot think of hashes as compression algorithms because...
हेलो बॉय 1 घंटा हो चुका है आपका 1 hour कंप्लीट
So can you mute yourself? I think there is a problem. Okay. So like I was saying, right, it should be extremely difficult to go back from a digest back to the original message. And that is why, like you rightly pointed out, because of the problems with decompression or rather getting back the same message, hashes cannot be used or considered as compression algorithms. Awesome. With that said, Raghu, do you want to have a 5 minutes break? And
yes,
what about you?
We are at 3:46 now.
Yes.
Maybe we take a break till 3:50. Right, say a 5-minute break and then come back because we have quite a bit also to be covered.
So thank you very much.
Take a logical break.
4
we'll
minutes.
Meet at 3:50. Yeah.
Sure. Thank you.
Hello.
Hi. Yeah, we can hear you.
Sir, can you go 2-3 slides before this one? I have a doubt in that slide.
Sure, absolutely. Let's do that. Let me just click over here. This one?
No, sir. Like the blockchain one.
Yeah.
Yes, sir. So, sir, what are we trying to compute here? Like on all these blocks, are like we are feeding the input of one into the hash.
Correct.
So, like, what is the end goal? What we are trying to achieve here?
Okay. So, what you have to achieve in this case is there are certain fixed values. For example, I'll try and break it down for you. Okay. So, timestamp, payload, and the hash of previous block. Okay. The payload would have all the transactions that happen. Timestamp is the timestamp, and then you have the hash of previous block. Now, for a miner, they have to
GE.
Okay, no problem. So for a blockchain miner, they have to calculate the value of nonce, just like you did in that exercise. Okay, there are certain things which are static. For example, Matthews Cryptoland, right? Then you have a certain variable part such as n, and you have to identify the value of nonce such that the hash of this block comes out with a few leading zeros. So that is what you're trying to achieve.
Yeah, sir. Okay, I got it.
Thank you. Okay, then it's 3:50. If you all are back, I think we can get started. Maybe I'll wait for a few more seconds and then I'll get started. Okay, let's get started. So far, we discussed about hashing, some of the areas wherein hashing is applied and used in the industry. Let's now move and switch gears to symmetric encryption. So when we talk about crypto systems, you would typically hear people talk about two different categories, symmetric and asymmetric. Let's have a look at each one of them. So what do we mean by a symmetric crypto system? Again, we have Alice and Bob. What they do is they exchange this key with themselves. Okay, so that's the key. When Alice has any message which has to be sent over to Bob, she uses that key, which is the same with Alice and Bob, to encrypt that message. Now, once the message is encrypted, she sends that over to Bob. Bob, once he receives that message, uses that same key to decrypt the message. Okay. So, and this is really what is called a symmetric cryptosystem or a symmetric encryption in this case, which is both the entities, the sender and the receiver, the encryptor and decryptor, they use the same keys. Now, the sender uses that key to encrypt the message and sends that encrypted message. The receiver gets that encrypted message or ciphertext, uses the same key to decrypt and get the clear text message back. Which brings me to the initial discussion or the question that was raised initially, which is Hmac same or is a bit different from encryption? If you remember, in Hmac, we were sending the Hmac along with the original message in clear text to the receiver. So Hmac was being sent along with the message. In case of encryption, it is only the ciphertext message which is being sent across. Okay. So this was a very brief, high-level view about symmetric cryptosystem. Let's have a look at probably one of the best symmetric encryption schemes and a lot more simpler as well, which is called as one-time pad. The way a one-time pad works, and as the name says, it's a one-time pad. So the pad must be used only once. The pad in this case can be your key. Okay, the key which is being used to encrypt and decrypt. Consider this over here. Let's say you have a message that has to be encrypted, which is a combination of ones and zeros. So it's 100110111 and so on and so forth. You select a random pad value over here, okay, which is like 01100, and then you do some mathematical operation on the message M and the pad. So in this case, let's say we do a XOR operation. Okay. So XOR typically would mean 10 is 1, 01 is 1, then 00 is 0, and 11 is 0. So when you do the XOR on the message M and the pad, what you get in return is a ciphertext. Okay, the encrypted block. Let's do a test around this. So Alice, it just wants to test the one-time pad if it's working fine with Bob. So the message that she has to send is hello. We just encode this into digits. So H becomes 7, E becomes 4 based on their displacement. Okay. Okay, no problem. So that's your message. Okay, and then you select a random key. Okay. Once you select the random key, what you do is, I think so. Can you mute yourself, please?
तन्मय, दीप, प्रथमेश, निहार, जतीन, क्या है कैमरे क्यों बंद है आपके? हाँ, हो गए पेपर हो गए क्या आपके?
I'll move it. So what you do is you add the message along with the key. Okay, so essentially M plus K. And what you get in return is 30, 16, 13, 21, 25. On this, you do the mathematical operation of mod 26. Okay, so essentially 30 mod 26 means 4, 16 mod 26 is 16, etc., etc. So when you do mod 26 on this M plus K, what you get in return is the ciphertext. So in this case, it's EQNVZ. When Bob gets this ciphertext, okay, remember, they already have the same key. That's the prerequisite, that both the parties, the sender and the receiver, must use the same key. And they have to identify a secure method of doing that, because that's the assumption we are having, that both of them already have the same key. So Bob gets the ciphertext message, encodes that into digits, and then applies the key on that. In this case, he performs the opposite operation, which is a C minus K. Once he does C minus K, he applies the same mathematical operation, that's mod 26, and in return, he gets back the same clear text message, and that is hello. So that means the scheme works perfectly fine between them. Alice and Bob had the same key and used one-time pad to essentially encrypt and decrypt the messages. Now, there are some issues with this scheme though. Can you guess any issues? Can you think of some issues with the way one-time pad is being implemented? Anybody want to unmute and share their opinion? No problem. Let me share that. The first issue is key length. If you noticed over here, the key length has to be exactly the same length as that of the message that has to be encrypted. Now that's a big problem. You can have much larger files, and then this means you'd have to use the key length, which is the same length as that of the message, right? So that is why if you want to use this, you'll have to use a high quality DRBG. Okay. The second one is the known plaintext attack. Now, what do I mean by that? Is the assumption for a known plaintext attack is that the attacker has the means to inject a message and capture or wiretap the ciphertext that comes out. So the attacker can send some message through your encryption scheme, so he already knows what the message he is sending, and can also capture the corresponding ciphertext that comes out of the encryption scheme. So in this case, the attacker is able to inject the message hello, and also wiretap the encrypted or ciphertext message, that's EQNVZ. Once the attacker has both of these, okay, the message and the ciphertext, he can actually do an operation with the known message and ciphertext by doing a C-M and then apply the same operation mod 26. And what he gets is the key. Okay. And this is the reason we say a one-time pad should always have a pad that's only meant for one time. Once you send it, once you encrypt a message with a one-time pad, change the key. Do not reuse the key. Because if an attacker is able to wiretap the ciphertext and inject a message into your crypto scheme, they can figure out the key which was used to encrypt it. So it's always recommended, if you're using one-time pad for any of your programs or anything of your applications, do not reuse the key. Now, with this said, we just looked at one of the possible schemes of Symmetric Cryptosystem, that's one-time pad. Let's look at another one. This one is called a Caesar's Cipher, or some of you might have heard about ROD 13, right? And this ties back to the initial challenge that we had of breaking the code, wherein we had a ciphertext and we had asked you to break down the code and tell us what it means. And the answer was Alice and Bob in Cryptoland. So what do we do in Caesar's Cipher is you look at a message, let's say A, you rotate that by a few numbers. So English would have 26 characters. So you rotate it by, let's say, 13. So A becomes N, B becomes O, and so on and so forth. Okay. So hello becomes URYYB. And that is essentially ROD 13. You can change it by one character. So A becomes B, B becomes C, C becomes D, etc., etc. And that is really Caesar's cipher. Okay. So I have to show you really quickly. Let me do that. Let's do this. So I'll do Python Caesar. Let's say the message is ABC. I want to rotate it by 1. the message becomes BCD. Okay, and so on and so forth. So if you want to say, let's say Cisco, and rotate it by 6, it becomes IOYIU. Okay, so that is Caesar cipher. Once you get it, if you know the shift pattern, it's very easy to go back to the original message. So in this case, the key is the displacement. Okay, are you displacing the characters by 1, by 2, in case of about 13 by 13? Okay, so that is Caesar cipher for you. And that brings us to the next mission. For those who already did the initial activity, it will be a lot easier. So Alice got access to Mallory's password, but this password is encrypted. Now, Alice has obviously done a lot of research on Mallory and what all algorithms she uses. And she knows that Mallory must have used a Caesar cipher. The encrypted password is this. Okay, now Alice really needs your help. Help Alice find the password. Maybe we'll give you 2 minutes, and let's see if somebody can shout Eureka.
Again, right, this is very much in line with the first guess that we had asked for, the title of the presentation. So you can take that as a hint.
I think we just got the answer. Thank you very much. Would you like to share the answer? Unmute yourself and share the answer, please. Okay. They're having internet issues. That's fine. But the answer is, I am Mallory and I hate Bob. Okay. And let's see. Anybody else who was able to solve this and wants to share how they did that? Anyone? No problem. Let's do that. Let me do that for you. So what I did over here is...
Nathan, we do have an answer. It says shift by 9.
Shift by 9?
Yeah. We'll look into what is the exact shift and what's the value. The answer is 8. That was a typo.
Okay, let's see. So the way you do this really is you have the ciphertext, but you do not know by how much has that been shifted, right? So you can do some kind of brute force attack. So let's do this, okay? I'm just going to do Python and run my script. The message that I like to decrypt is this. Let me do this. So what I do is I just printed and displaced by 1 and then printed the value. Okay, and that's over here. Now, knowing Alice, Bob, and Mallory now, right, I do have some context about what they can possibly be using, because a lot of times the passwords that we use is our date of birth, our names, a name of somebody we know, some family member, somebody we hate, maybe, right? So I just stream through this, and something that catches eye is this. Shift pattern 18, it says, I am Mallory and I hate Bob. And I can very easily relate to this, that Mallory, knowing she thinks she rules crypto land and knowing she knows Bob is after her life, she might have used his password, right? So what this really means is if we are using words such as this, our name, somebody else's name, for somebody who knows about us and somebody who can do social engineering, right, and gather information about us, if we are using such words in our password, it is a lot more easier to identify your password than imagine if Mallory had really used this as a password, right? We would not have been sure about that because it looks odd, right? But because Mallory used a word and we can relate to that word given the context and given what we know about Mallory, it is safe to assume that if we have to try and use the password, that's the first one we'll go and try. So that's the brute force we just did on a Caesar's ciphertext, which was shifted by a pattern of 18. Okay. With this, we'll move on to the next one. Now, given the time, we cannot cover all the or most of the encryption algorithms. So we did cover one-time password, Caesar's cipher, and then we look at AES. We're going to skip DES for now. AES, it works on blocks as opposed to the one-time pad, which we saw earlier, which typically works on bits. Okay. Here, the key size is good enough. It starts with 128 bits and goes up to 256 bits. Compare this to a one-time pad. A one-time pad would have a super large key if you have a super large message which you're trying to encrypt. Okay, 128-bit seems a very reasonable value compared to directly being proportional to the message length that you're trying to encrypt. If you compare this to another cipher, which is DES, DES uses only a key of 56 bits. So when we say that DES is insecure, right? That's what we always say. We always ask our customers to move away from DES. Okay. And always use AES. The reason is that DES only has a key of 56 bits. So if you have to explore all the keys and then possibly run it against the ciphertext to, let's say, do a brute force attack, okay, you only have to explore 2 to the power of 56 keys because that's the key range because you have a 56-bit key. Compare that to AES, it starts with 128. Now, if you compare 2 to the power of 56 to 2 to the power of 128, the difference is huge. It's so huge that per NIST, if a machine is able to crack a DES ciphertext in 1 second, which is a 56-bit, it'll take the same machine 149 trillion years to crack a 128-bit AES. Now that's the difference. We're talking about from 2 to the power of 56 to 2 to the power of 128. And that difference is huge. So unless we break the algorithm by some means, exploring the key space is not really possible with classical computers. So having said that, when we look at the modes of operation, you would have heard about electronic code book or cipher block chaining, CBC, or counter mode. Let's have a very quick look at what these are. So in my extreme left of the screen, we have an image of a penguin. The message and ciphertext in this case, both are same. So that is why the image is super clear. And we can easily say it's a penguin. And like we discussed earlier, in the case of AES or even 3DES, it works on blocks instead of bits like one-time pad does. So in this case, let's talk about ECB, okay, the electronic code book. We take the message M, we break it down into a couple of blocks. So let's say the blocks come out to be 1, 2, 3, 1, 4. Now, individually, we encrypt these blocks. So the output comes out to be 59153, with each of these 5 being one block. If you notice, if you look at the image below, although it's not exactly the same, it's not very clear that's a penguin, but the pattern is very clear. Now, we humans are very good at pattern matching. If we are good at that, imagine what the machines can do, right? So if you notice over here, the pattern that was there in the message M, the same pattern is continued in the ciphertext C. Just that 1 became 5 and 2 became 9, and then we have a repetition, right? So the same pattern repeats in the ciphertext as well, and that is why we can easily say that, you know what, it's a penguin. And that is why you would see it's always recommended not to use ECB. Compare that to CBC or CTR. If you look at the image, that's just plain noise, right? It is almost impossible to say that the original image was that of penguin. What we do in CBC, for example, or rather in CTR as well, is we use the initialization vector. Remember, we use that in Merkle-Dumgard construction as well, when we were looking at how the hash is calculated. So in case of a CBC, we break down the message into blocks. We use our initialization vector, and we XOR the initialization vector with the first block. We encrypt that. The output, what we get from this, is fed as an input to the next block. We do a XOR on that and then encrypt that. And then we repeat this cycle. So again, just like we saw earlier, we are chaining it. The output of the operation on every block serves as an input to the operation on the next block. So that is CBC. If I talk about the CTR mode or the counter mode, we take an initialization vector and we increment that to the number of blocks that we have. So in this case, we do IV plus 1, plus 2, plus 3, plus 4. Now we do an encryption on these IV, okay? When we do an encryption on this IV, we get a random string or a pad maybe, which is the same length as that of the blocks that we have. Okay, so what you're getting is essentially a one-time pad, what we just discussed earlier. Now, like we did earlier, we do a XOR operation between this one-time pad, which is derived from the initialization vector, and the message M. And the resultant operation is the ciphertext message. So the disadvantage of a counter mode can be that you cannot use the same IV, because that would mean that you'll get the same one-time pad. And like we discussed earlier, a one-time pad, we should always avoid the reuse of a key. The advantage of a CTR really is if your hardware supports parallel pipelines, it can be really fast. If you look at the CBC mode, to encrypt the second block, I have to first wait to complete the operation on the first block. To complete the operation on the third block, I have to wait to complete the operation on the second block. In case of a CTR, I really don't have to wait. Everything can happen parallelly. And that's the advantage of using a CTR mode if your hardware supports parallel encryption pipelines. So that's the crux. One thing, if I wanted to take away from this, is do not use ECB. Not so good. CBC and CTR can be used. It depends on what are your requirements. And if you want, if you have a hardware that supports parallel pipelines, then you can definitely go for CTR. With this, we come to the next section, which is asymmetric crypto system. When we look at the symmetric crypto system, one question that arises, if you see the assumption that we made over there, is both of them, Alice and Bob, should already have a pre-shared key with them. And that same key is used to encrypt and decrypt. Now, the question is, if you could have exchanged the keys securely, why couldn't you have exchanged the messages then? Because we are assuming that there is some way of exchanging the keys securely. Now, one way of looking at this is Alice calls Bob and they exchange the key over a telephone call. Obviously, that's not so secure, right? And that's a big problem. When it comes to using symmetric crypto systems, they are fast, no doubt in that. But the assumption that they work on is that they need a key to be there, which is pre-shared. Or somehow we derive the keys that are same on both the endpoints. And that is precisely where asymmetric crypto system comes into picture. In case of asymmetric crypto system, let's say Bob has a pair of keys. A private key, which is the red one over here, and the public key, which is the green one over here. Now, if Alice and Bob want to communicate, what Bob can do is Bob can send over his public key to Alice. Once Alice has the public key of Bob, if there's a message that she has to encrypt, she can use Bob's public key to encrypt that message. And then she can send that message over to Bob. Bob, when he receives the encrypted message, can use the corresponding private key to decrypt the message. So what this means, if you compare this to a symmetric crypto system, a symmetric crypto system only had one key. The same key was being used to encrypt and decrypt. On the other hand, in asymmetric crypto system, it has a pair of keys. Now, the way these pair of keys are used is they are mathematically linked to each other. And if you want to encrypt a message, use the public key. If you want to decrypt that ciphertext message, use the corresponding private key. And what we just discussed, this forms the basis of what we call as PKI, or public key infrastructure. When you browse a website, it presents a certificate to you, right? So let's look at what forms PKI, what is the basis of PKI. So the basic public key operations, if we can say, there are two sets of keys like we discussed. One is a public key, and as the name says, it's public. It can be given out, it can be distributed. The other is a private key, and because it's private, it has to be kept secret. The public key can be used to encrypt the data. The corresponding private key can be used to decrypt that ciphertext data. On the other hand, there's another operation. Let's say I am buying a property from Raghu, for example. I go on that site and I call Raghu. And I say that, Raghu, everything is good. I would buy this property from you. And Raghu is all happy because he wanted to sell that property. But then after some time, I say, you know what? I never told that. I never said that I want to buy this property. Is there a way for Raghu to really pinpoint and say, you know what? No, you actually said that. And that is where digital signing is used. Can we use it for non-repudiation? Okay. So for example, if somebody has a message that they have to sign, that they have to prove that I really sent this message, they can sign it. In case of signing, a private key can be used. Okay. Then if somebody has to verify, if Raghu has to verify, so if I have to tell him that I'm buying his property, I'll send the message and I'll send a signature along with that. A signature is what proves that I really said that. And I'll do that through my private key. Now I'll give my public key to Raghu. And if Raghu is able to verify the signature using my public key, that means that I must have sent it. Okay, so a public key can be used to encrypt the same message. Ciphertext can be decrypted using the private key. On the other hand, a private key can be used to sign, and the corresponding public key can be used to verify. Now let's look at the RSA algorithm. As you would know, the cryptographic algorithms are based on prime numbers. So what we do over here is we choose two random and large prime numbers P and Q. Now we compute the modulus n, which is nothing but the product of these two prime numbers. Okay. Then we compute a quotient function, and after that we compute two exponents. One is called a public exponent, the other one is called a private exponent. So when we say a public key is a function of the modulus, which is the product of these two prime numbers, and the public exponent. The private key is a function of the modulus n and the private exponent. So when we talk about these cryptographic algorithms, right, if you notice, what we are relying on is it is very easy to compute the product of two prime numbers. Very easy to compute n, but it is very difficult to factorize it into prime numbers. Okay, and that's the mathematical difficulty over here. So public key is a modulus of n and e. A private key is a function of n and d. So when we have to encrypt a message m, we use the public exponent e. So it becomes m to the power of e mod n. What you get is a ciphertext message. When the receiver gets that ciphertext message, they can use the private key, which is the private exponent. So c raised to the power of d mod n, and that gives back the clear text message m. Similarly, if somebody has to sign, they can use the private exponent, and when that signature has to be verified, they can use the corresponding public exponent. The takeaway is when you have two keys in an asymmetric crypto system, they are mathematically linked to each other. Now, the way they are mathematically linked is what was done by one key, it can only be undone by the other key. If you can encrypt a message by a public key, only decrypt that using the private key. The next is what can be undone by one key. It had to be done by the other key. If you are able to verify a message using someone's public key, that means the message was definitely signed by their private key. And that really forms the basis of PKI. In PKI, you'll have an entity which is called as a certificate authority.
One small thing, just to add on, if you look at the entire RSA algorithm, right, all the parameters that Nitin explained, they are generated out of what we call as two basic entities, which is P and Q. Now, while you would see most of the literature mentioning that, sorry?
Public key infrastructure.
Correct.
So while P and Q are supposed to be prime numbers, the catch there is they don't have to be prime numbers by themselves. The condition is they have to be co-prime with each other. A small example is 3 and 8. the value of P can be 3 and Q can be 8, and the RSA would still work perfectly fine because 3 and 8 are co-prime with each other, which ties into a fact that HCF, the math that we used to learn in school days, LCM and HCM, highest common multiple, if that is 1, then two numbers are said to be co-prime. So that's another condition for P and Q. They have to be co-prime. Over to you, Nitin.
Thank you. So, like Raghu said, prime numbers, they are the magic behind almost all the cryptography that we do, right? So, coming back to PKI, there's an entity called a certificate authority, which is responsible to issue certificates. And when you go to website, you will see it will have a certificate, right? Let's have a very quick view of what a certificate really is and how is it formed. So let's say we have a web server that hosts the Cisco.com website. Okay. So we'll go to a well-known CA and request for a certificate. And that is called as a certificate signing request. Now, the CA would issue a certificate to us that proves for somebody who's visiting that indeed this website or this web server is Cisco.com. Our certificate would have two portions. One is a data portion. The other one is a signature portion. If you look at data portion, there will be certain attributes like serial number, validity periods. The certificate is valid from today to next 2 years, for example. Issuer CA identity. Who issued this certificate? Then subject identity. Who is this certificate issued to? So in this case, maybe it's issued to Cisco.com. And the certificate would contain the subject's public key. Okay. So like we discussed earlier, a public key can be distributed. The way a public key is distributed is by giving out a certificate, because a certificate contains the subject's public key. And then there'll be a few attributes like what can this certificate be used for? Can this certificate be used for TLS web server authentication? Or can a certificate be used for TLS client authentication, etc., etc.? What is TLS and the TLS handshake? We'll actually do that tomorrow. So in all, a certificate will have a data portion that will have information about to whom is this certificate issued and who issued this certificate, along with the subject's public key. Now, like Raghu said, whatever we are studying in the initial parts, it is being used in the other parts. So in this case as well, once we have this data portion, we serialize that and run that through a one-way hash function, and hashing comes back. So we serialize all of this data content, and once we have it, we run it through a one-way hash function. What we get is a certificate hash. We sign that using the CA's private key. Remember, you can only do a signature or sign something with your private key. What you get is a signed hash value, which is appended to a certificate. And that becomes the signature portion of it. Okay. So when you go to a website and it presents a certificate to you, essentially you are looking at that, and then to verify that, you use the corresponding CA's public key. Because if you're able to verify that, that means it must have been signed by the CA that you trust. So the entire PKI model is based on trust relationship. The way we trust something is a well-known authority signs the data, and the public key of that CA is well known. That's why you import a CA certificate. And then you can use the CA's public key to verify that signature. Okay. And that's the use of certificates over here. If I very quickly show you, just 1 second. So this is Cisco's website, right? If I go over here and say certificate, if I click on details, if you see, that's the subject name. The certificate is issued to Cisco.com. That's the issuer name. Who issued this certificate? This is the certificate serial number. And then you have the signature algorithm. Which hash algorithm was used to sign, to create the signed hash? And in this case, it's SHA-256. The certificate is valid from and valid to this date. So it's a 1-year valid certificate. And then you have the subject's public key. Okay. And what can this key be used for? So this is how a certificate is used. Okay. So let's go back to the presentation. So like we discussed, that's the certificate data portion, and then you have a signature portion, and this one will tell you what hash algorithm is being used. Next, can you please mute yourself, guys? Request everyone to mute themselves.
Hey, guys, if you unknowingly have unmuted yourself, please be on.
I think even I got muted. Raghu, can you hear me?
Yeah, I can hear you.
Thank you. So we just talked about symmetric encryption algorithms. We said that it's very fast, but the assumption is that it needs the pre-shared keys. So what can we do to exchange, or rather, and we all agree, it's not safe to exchange the keys over an insecure medium such as internet, right? How can you send a key securely to the other side? So the algorithm Diffie-Hellman comes to solve this. The idea behind Diffie-Hellman is to be able to derive the common session key across an insecure medium. And this also uses asymmetric cryptosystem. So let's have a look at this. Alice and Bob, they want to use, let's say, AES 128 for encryption. Okay. But they have to derive the pre-shared key now, because there is no easy way to send that pre-shared key K. So what Alice does is she selects a generator G and a modulus P. Now she picks up a random number, that's A, which is Alice's DH private key. Okay. And now she computes the corresponding public key. And that is G to the power of A mod P. So she uses the generator G modulus P and the private key for that. She computes the public key and sends that along with the group definition. So you would see DH group 19 being used, for example, or group 14 being used, for example. There's also group 1, group 2, group 5, right? So the group definition would define the generator G and modulus P. So Alice doesn't send her private key. She only sends her public key and the group definition. Now, the mathematical complexity over here is knowing the public key, the generator, and the modulus P. An attacker cannot derive the private key. And that's the mathematical difficulty in DH. Okay, and that's what it really runs on. So once this is sent, Bob would use the same generator G, the modulus P, and pick up his own private key. That's called B over here. Using that, Bob computes his own public key. And now Bob sends his public key to Alice. So if you notice over here, both of them kept their private DH keys as secret. only send their DH public keys. When they receive each other's public keys, the beauty of Diffie-Hellman is that using that information, they can derive a common secret key. They never exchange the private key. Okay, they only exchange their DH public keys and came to an agreement of using the same session key or derive the same secret. Now, once this is done, this can eventually be used as an input or rather the key to be used for, let's say, AES encryption. If you look at any practical implementation like TLS, like IKE version 1, Internet Key Exchange, IKE version 2, all of them, they use Diffie-Hellman or ECDH, that's called elliptic curve Diffie-Hellman, to eventually derive or come to a common session key, which is then eventually used by a symmetric encryption algorithm like AES. So that's the beauty of Diffie-Hellman. It lets you come to a common, derive a common session key over an insecure medium. And this is used in almost all of the crypto schemes that you see, which are most prominently used. Like I said, TLS, IKE version 1, IKE version 2. With this, we come to a logical end of asymmetric crypto systems. And what is left is the random number generation. So moving on to that, Raghu, you want to take over?
Yeah. So I know it's quite a lot technically when we cover encryption, hashing, Hmac as part of one particular session. But we'll conclude the session with something very light. That is random number generation. Now, for this particular section, the first thing is a question that I have for everybody. Right? We always say that let's use a random number n. Now, while we have been using the random number n without giving it much of a thought, the security associated with the cryptographic strength, right? The strength of the algorithm depends on the random number that is being used. What if the random numbers that are generated are not truly random and they just follow a pattern? It would be easier for an attacker to compromise a crypto system because now they can predict what the next random number that the algorithm will use or the system will use for generating further keys. Hence, the selection of random numbers becomes very, very crucial. And of late, we have seen multiple attackers, security researchers finding out a pattern in which our existing systems for random numbers to be generated are used. Hence, we came up with a concept called pseudo-random numbers, where we do not want to commit into the fact that they're truly random number, but they are pseudo-random numbers. Now, this particular scenario led to the opportunity of how can I ensure that the random number I'm generating is 100% random and there is no probability of the same system generating the same random number twice. Goes back to our concept of hashing, right? No two input files should generate the same hash. Similarly, in case of random numbers too, the system should not generate the same number multiple times as random number. Nathan, if we can quickly move to the next part.
Raghu?
Hey, the system muted me again. Okay, so now for everybody, we are going to watch a clip from a very popular series called Game of Thrones. Just concentrate on the character which is about to run, right? The small kid. So he is set free with a small prerequisite that he has to reach the other end while the character on the screen now would attempt to kill that guy, right? With a bow and an arrow. Now look at the character running, right? Now for most part of this particular clip, you would see that the character is running in a straight line. Let's just give it a second. So this character here would try to kill the character running by shooting arrow. And if you look at the character, right, that small shadow, he's running in a straight line. What does that basically mean here? It gives the attacker more certainty to ensure that when he tries to compromise something, it is easier. Now, within this scenario itself, if the character here would have not run in a straight line and he would have followed a random nature while running, it would have made the person shooting the arrow a little more difficult, right? Because now he doesn't know the predictive behavior associated with him running. That is the significance of random numbers in cryptography also. The use of random number adds that uncertainty and complexity, which makes it difficult for the attackers to break the cryptographic algorithm and hence increases the strength. That is the reason why we wanted to have this small clip shared, signifying how random is truly random. Now, we all used mathematical functions for generating random numbers by using modulo, right? A modulo 100 to generate random numbers between 1 to 99, modulo 1000 till 999, so on and so forth. But the true randomness is something that was not achieved by it. So a company named Cloudflare started a research project called as Lava Rand. What this did was, rather than using mathematical functions in order to generate random number, they used the entropy associated with lava lamps to generate random numbers. Now, as we know, entropy associated with the lava lamp, they are truly random in nature, and hence the random number that is generated out of this is truly random in nature. And you would see a research link also mentioned in the slide below that gives details on how random numbers are generated using lava lamp. Now, to make this entire thing more complex, recently, in the past few years, we have seen quantum computers are also being used to generate random numbers, thereby increasing the overall strength of the cryptographic algorithm by ensuring that the random number generated is truly random in nature. Now, with that said, if there are any questions, feel free to ask them. We are monitoring the chat. If somebody wants to unmute themselves and go ahead and ask the question, now would be a time.
Sure.
So, am I audible?
Yeah.
Yes.
So, actually, you brought up quantum computing, so I was slightly interested towards that. Actually, I wanted to ask this question earlier as well. Won't quantum computing make it much simpler to hack into systems? Like even blockchain, for example.
Oh, yeah. So, what you're asking directly ties to what we're going to discuss tomorrow. The answer is definitely yes. quantum computers do pose a big threat to the current algorithm that we used for encryption, decryption, and precisely, if I have to be precise, it does pose a major threat to asymmetric cryptosystems, RSA, and the key establishments, for example, Diffie-Hellman. It does pose a threat to them because it ties into the fact what we discussed earlier. We always so to compute the product of a two prime numbers is super easy. It's super difficult for a classical computer to compute or factorize a product, right? So quantum computers do that with ease, and that is why they pose a big threat to the way or to the current algorithms which are in use. But this really ties into what we are going to discuss in detail tomorrow.
So I'll just give a quick overview, right? Appending to what Nitin already mentioned. The strength of cryptographic algorithms are not increasing over a period of time. However, the computation power is increasing with time. This ties into the keynote session we had when Suhas was speaking earlier in the day. The rate at which we are embedding more and more silicon onto the chips is exponentially increasing. The latest Apple chip has around about 1 billion transistors in it. Now, what has happened is increase in computation power has always posed a threat to the mathematical computations that are used to build cryptographic algorithms. The stronger the computation is, easier it will be to break a cryptographic algorithm. This was all fine with classical computers. Now, to add on to the problems, we came up with something called as quantum computers, which operate way faster than what a classical computer can do, thereby decreasing the time that it takes to complete the same mathematical computation. And from a security standpoint, and Nitin would agree on this, is there can never be 100% secure system. It is always about building security algorithms, security mechanisms in place, which will take the intruder or the attacker or adversary longer amount of time to crack it. It is always the play between the amount of time that it takes for the attacker to compromise a system. If the amount of time taken by the attacker is higher than the reward that they would get as part of it,
correct,
you can safely assume that you have built a secure system. Because then there are concepts of constantly changing the keys, like a Diffie-Hellman where Nitin mentioned, right? We can constantly change the keys. So even if somebody tries to compromise the system and they get access to the key, the very next moment the key is changed. Now, because the computation itself took time, quantum computers would attack this basic premise. The computation is so faster that you would not have a system with the existing algorithms that are foolproof to ensure that you are giving the amount of time the defender of network would need if he has to secure the system. More on this regarding how quantum computer pose a threat to cryptographic algorithms and what are the cryptographic algorithms that are as of now considered secure from a quantum computer perspective. Now, as we speak, if somebody designs, say, a extremely powerful quantum computer, the algorithms we know of currently that are safe or considered to be safe from quantum computer would be broken again easily.
Yep, and just the difference would be that we'll look at that tomorrow. Some algorithms would be absolutely insecure. Some can be partly secure. And again, this is, I'll say can be. The reason is we are not 100% sure yet. We haven't really reached that stage yet wherein we can pinpoint and be 100% sure that this is going to be quantum resistant. but the math behind some algorithms, it does look like it would be quantum resistant. And the math that is used in the current algorithms, it's safe to say some of the algorithms like Diffie-Hellman and RSA would probably be no longer secure once we have a good general purpose quantum computer.
Thank you.
I think the catch there was general purpose quantum computers.
Yeah, this is a really amazing talk. We are really overwhelmed to see the depth and breadth of the complexity of cryptographic system. Of course, students can very well understand. Nitin, I just had one very quick question. Quantum computers are a threat. Quantum computers are a threat to cryptography, right? However, why supercomputers had never been a threat to this?
So the way I see it, the very basis of quantum computers or what they are based on is very different from a classical computer. Let me use an example for this. Okay, think about the classical computer as a candle. Okay, now think about quantum computer as a bulb. You cannot ever achieve a bulb by improving a candle, because these are two very different technologies, right? Now,
is it the speed of the computation even after even a supercomputer cannot crack?
So, as of now, supercomputer, the way it's based on the principles, right? It's still not based on the quantum mechanics, correct? If you see the principles which really a quantum computer is based on, these are very different compared to any classical computer that we might have, right? The use of qubits, superposition, for example, entanglement, for example, right? These are based on the concepts which are very different from what we are used to seeing in the nature with the naked eye.
Eventually, they will still be operating in 0 and 1. Or are they going beyond that?
So they work on qubits instead of bits. The beauty of right,
but don't they use? Would the binary concept itself will change?
So the way you have to see it, right? Binary. When we say binary, we are talking about 0 and 1, and that's about it. It can be 0 or 1, right? Whereas things change when it comes to quantum, because it can be 0 or 1 at the same time, unless you measure it, correct? So this property, it changes everything. The way things are, it changes everything.
So that simply means that I need to update, right?
Okay, so we're going to discuss a lot more on this tomorrow.
Yes. I would look forward to listen all that.
Yeah, but the basic thing was, and this is what me and Nitin were discussing yesterday, when we looked at certain courses that are available online on quantum computing, the one is they make it sound very complex, which it is, but not to that extent. The basic principle is our classical computers at any given point in time understood if it was 0 or 1. Whereas in quantum computing, it can be 0, 1, or 0 and 1 at the same time.
So the way I'll say, sir, is quantum computers, they are very good at certain things, like as opposed to a classical computer. Right? For example, if you have a problem that only has one solution, quantum computers are very good at that. They are not good at, let's say, sorting, for example. They are very good at searching, but not good at sorting. So any problem which requires a lot of parallelism and which has one correct solution, quantum computers really work the way out pretty well over there. And supercomputers being still based on the concepts of classical computing and not really quantum mechanics, and that's where the difference lies.
Okay. This is really good. So some much more simplified lecture has to be planned on quantum computer so that his students can very well understand what precisely is the difference, how it is going to bring a technological disruption. Right.
Yes, sir.
Yes. So this had been really great. These participants and students have been very much appreciating the content. They have been very interacting. And interestingly, they kept on shouting "Eureka, Eureka!" So that was another thing. So let's look forward to have another great session tomorrow. So, dear all participants, please join tomorrow at 9. Now onwards, all of our sessions will be starting at 9. All the participants, please spread a message among everyone that they have to join the session. Right? This is the best knowledge which you are getting so very easily and with an opportunity to interact with the leader himself. So make sure that you are finding good time to attend these sessions. Okay, thank you very much and have a great time. Bye. Bye,
Thank
Raghu.
you, everyone.
Good evening.
Thanks a lot.
Thank you, everyone.
Yeah. Bye.
Goodbye.